Hello everyone, and welcome to today's presentation. I'm excited to share with you our topic, Pitting Corrosion Evaluation for Piping, a practical example as per API 570 and API 579, 1 ASME FFS-1. In this session, we'll explore what pitting corrosion is, its causes, and why it's critical to assess its impact on piping integrity. We'll also look at the key standards that guide us in inspection and fitness for service evaluations. Next, we'll review a real-world case study. We'll look at a scenario where inspection data was collected to evaluate pitting corrosion, focusing on a Level 1 assessment. This example will help illustrate how we interpret data, identify the severity of pitting, and determine our next steps based on the findings. Finally, we'll wrap up with our conclusions and recommendations. This includes key takeaways from the case study and how we can improve our inspection strategies to better manage pitting corrosion moving forward. Overall, today's presentation aims to equip you with the knowledge to better understand, assess, and address pitting corrosion effectively within your operations. Let's talk about the challenge of pitting corrosion. So, what exactly is it? Well, it's a localized form of corrosion that forms small, deep cavities or pits in the metal surface. Unlike uniform corrosion, which wears down everything evenly, pitting is much more insidious because it's much harder to predict how quickly these pits will penetrate the material. This unpredictability makes it particularly dangerous. In fact, pitting can lead to rapid and unexpected through-wall failures, which means the metal can suddenly fail without much warning. This poses a significant threat to the integrity and safety of process piping systems, which are critical in many industries. Recognizing and understanding pitting corrosion is essential in our efforts to prevent costly failures and ensure safety across our operations. Let's talk about the governing standards that guide our piping integrity management. First up is API 570, the Piping Inspection Code. This is our primary reference for inspecting, rating, repairing, and altering piping while it's still in service. Next, we have API 579-1, also known as the ASME FFS-1, which is our detailed engineering handbook for assessing flaws. It provides a multi-level assessment approach, Level 1, 2, and 3, so we can determine the safety of a component based on the extent of the damage. Connecting these standards, we get a comprehensive framework. API 570 guides our inspections and evaluations, and API 579-1 provides the detailed assessment methods. Let's take a closer look at this case study involving scenario and inspection data. During an external inspection, widespread pitting was discovered on the outside surface of the cylindrical straight section of a piping component. Now, this pipe is made of SA 106 grade B steel and was constructed according to the ASME B 3013 code from 1992. Our task here is to determine whether this pipe is still acceptable for continued operation at its current maximum allowable working pressure, MOP, and temperature. For simplicity, let's assume the pitting damage has been arrested, meaning no further deterioration is expected. Also, there are no additional loads acting on this section. Looking at the data, the outside diameter of the pipe is 168.3 millimeters, with a design condition of 17.24 bars at 150 degrees Celsius. The nominal wall thickness is about 10.97 millimeters, but the maximum pit depth observed is 5.6 millimeters. Importantly, there's no uniform metal loss, and the future corrosion allowance is 0.76 millimeters. The weld joint quality factor is perfect at 1, indicating a seamless pipe, and the allowable material stress under these conditions is approximately 137.89 MPa. Lastly, the temperature coefficient, which accounts for material strength reduction at elevated temperatures, is 0.4. All of these parameters help us assess whether the pipe can safely continue to operate without risking failure due to the pitting corrosion. The key here is understanding how the maximum pit depth relates to the pipe wall thickness and how the material's stress capacity holds up, especially considering the elevated temperature. By carefully evaluating these factors, we can make an informed decision about the pipe's integrity and whether it remains fit for service. This process underscores the importance of inspection data and proper analysis in maintaining safe operation standards in piping systems. Let's walk through the pitting corrosion evaluation at Level 1 assessment. First, we need to determine some key parameters: DO, FCA, either TARD or TNOM, and loss. In this case, DO is 168.3 millimeters, FCA is 0.76 millimeters, loss is 0, and the nominal thickness TNOM is 10.97 millimeters. Since loss is 0, our remaining thickness, TARD, equals TNOM, which is 10.97 millimeters. Next, we move on to Step 2, determining the wall thickness to be used in the assessment. We subtract FCA from TARD, so TC equals 10.97 minus 0.76, giving us 10.21 millimeters. This is the thickness we'll use as the basis for further evaluation. In Step 3, we identify the area on the component with the highest density of pitting corrosion. This is based on the number of pits observed. We take photographs or rubbings of this area, including a reference scale, to accurately record the extent of surface damage. This visual documentation helps us analyze the severity more precisely. Finally, in Step 4, we determine the maximum pit depth, which we denote as Wmax. Here, it's 5.6 millimeters. To find the remaining thickness at the deepest pit, we subtract Wmax from TARD. So 10.97 minus 5.6 gives us 5.37 millimeters. This value indicates the thinnest wall thickness in the most affected area. Remember, TARD is the uniform thickness away from the damage, measured during inspection, and TC represents the future, more corroded wall thickness, considering ongoing corrosion. Understanding these parameters helps us evaluate the severity of pitting and assess the component's remaining integrity effectively. Now, let's move on to Step 5 in our pitting corrosion evaluation, which is the Level 1 assessment. Here, we need to determine the ratio, denoted as RWT, of the remaining wall thickness to the future wall thickness in the pitted region. Essentially, we're comparing how much of the wall is left versus what it should ideally be. To proceed, we check if the team criterion is satisfied and if the RWT value is greater than or equal to 0.2. If both conditions are met, we can move on to Step 6. If not, then the Level 1 assessment criterion isn't satisfied, which indicates a need for further evaluation. It's important to note that the limits on team and RWT are set to prevent local failures, such as pinhole leaks, which could be critical. For piping applications, the team threshold is set at greater than 1.3 millimeters. Remember, both pitting and general corrosion damage are acting on the same side of the material, and importantly, the pit depth exceeds the flaw's critical area, or FCA, which raises concerns about integrity. Now, to calculate RWT, we take the remaining wall thickness, team, and divide it by the original or future wall thickness. For example, if team is 5.37 and TC is 10.21, RWT becomes approximately 0.526, which is above the 0.2 threshold, so we can proceed. Moving to Step 6, if the equation isn't satisfied for an individual pit, meaning the RWT is too low, we evaluate that pit as a local thin area using a more detailed Level 2 assessment. Here, the factor Q, used to determine the length over which we average the thickness, is obtained from specific tables in the standards, based on the remaining thickness ratio RWT. Assuming the pit diameter, D, satisfies the criteria, we then determine the MOP, or maximum allowable working pressure, for the component, using the thickness determined earlier in Step 2. Finally, in Step 8, we compare the visual pattern of the pitting damage to the standard charts found in API 579-1, Part 6. These charts provide a severity scale from 1, indicating minimal damage, to 10, which is the most severe. Based on our visual assessment, this particular damage corresponds to a pitting chart grade of 4, indicating moderate severity. This systematic approach helps us evaluate the integrity of the component and decide on necessary actions to ensure safety and reliability. Now let's move on to step 9, calculating the remaining strength factor, or RSF. The RSF essentially tells us how strong a damaged component still is compared to an undamaged one. If the RSF is 1, that means the component retains its full strength. To determine the RSF, we look at the table shown at the bottom of the pit chart from step 8, which was based on the value of RWT calculated in step 5. Interpolation is acceptable if your RWT falls between the table values. In this case, we use the API 579-1 tables or formulas with a pitting chart grade of 4 and an RWT of 0.526. The calculation gives us an RSF of approximately 0.8815. Now, compare that to our allowable threshold, which is 0.9. This comparison helps us assess whether the corrosion damage is acceptable for operation. Moving to step 10, if the RSF is greater than or equal to the allowable RSFA, then the pitting corrosion is considered acceptable at the current MOP, which we determined in step 7. But if the RSF is less than RSFA, then the region of pitting corrosion might be acceptable only at a reduced pressure level, called MOPR. This MOPR is calculated using the equations from Part 2, paragraph 2422, and it uses the same MOP from step 7 as the basis for the calculation. In our specific case, since our design pressure is 17.24 bar and the calculated MOPR is 17.222 bar, the pipe actually fails the level 1 assessment. That means the corrosion damage is significant enough that we need to consider operating at a lower pressure to ensure safety and integrity. Let's wrap up with some key takeaways and recommendations. Pitting corrosion is a significant damage mechanism that we need to evaluate systematically to ensure safety and integrity. The API 570 provides a solid framework to guide our inspection process, and for more detailed fitness for service assessments, we turn to API 579-1. When conducting a Level 1 assessment, think of it as a conservative, step-by-step screening tool. The main goal here is to calculate the remaining strength factor, or RSF, which helps us determine whether the component is still acceptable for service. It's important to document any findings that are deemed acceptable and keep monitoring them over time to maintain long-term integrity. But if we find something unacceptable, that's a red flag that requires immediate action. This could mean performing a more detailed analysis, like Level 2 or 3 assessments, or implementing repairs, such as weld overlays or section replacements, or even making operational changes, like derating the piping system. The key message is that systematic evaluation and timely intervention are essential to prevent failures and extend the life of our assets.